consider the number of strokes, that is 2-stroke engine or 4-stroke engine. If, for example, if it is a 4-stroke engine, divide by 60, and also the number of cylinders, where K is the number of cylinders. Whereas for 2-stroke engine, PM LA N by 60, there is no 2 there in the denominator, into K, so many kilowatts. For calculating brake power, it is only 2 pi nt by 60, where T is in kilonewton meter. Whether 4-stroke engine or 2-stroke engine or multi-cylinder engine or single cylinder engine, the power is formula for brake power is same. IP minus BP is frictional power, which is a function of speed of the engine. Then we define mechanical efficiency as the ratio between BP by IP. This efficiency shall take into account the frictional losses that occur in the IC engine. It will be in the range of around roughly 75 to 85% based on the type of the engine. Mechanical efficiency is usually a function of RPM, or this rotational speed of the engine, because frictional losses vary with the speed. Now we shall define indicated thermal efficiency. It is defined as the ratio between indicated work done per second and the heat released due to the combustion of fuel per second in the combustion chamber. Where m dot f is mass consumption rate of fuel in kg per second, and LCV is lower calorific value of fuel in kilojoule per kg. Then the resultant formula for indicated thermal efficiency is IP by m dot f into LCV. Usually it falls around 25% to 30% for an internal combustion engine. Now I shall define brake thermal efficiency. It is defined as the ratio between brake work done per second or brake power output of engine and the heat supplied in the combustion chamber due to combustion of fuel. Brake thermal efficiency is brake power output in kilowatts divided by m dot f into LCV, where m dot f is mass consumption rate of fuel in kg per second, and LCV is lower calorific value of fuel in kilojoule per kg. Now we can here again define mechanical efficiency of the engine as brake thermal efficiency divided by indicated thermal efficiency. It is another definition for mechanical efficiency. Now we shall define specific fuel consumption, which is also abbreviated as SFC. It is defined as the amount of fuel required to produce, required in kg, to produce 1 kilowatt hour of work. It has got two formulations here, that is BSFC, brake specific fuel consumption, is equal to brake power fuel consumed in kg per hour divided by brake power in kilowatts. The resultant unit is kg per kilowatt hour. Similarly, ISFC, that is indicated specific fuel consumption, is equal to fuel consumption in kg per hour divided by indicated power in kilowatts. The resultant units will be kg per kilowatt hour. Because the denominator being more in ISFC, their ISFC will be lesser than BSFC. Numerator is same in both the formula, but the denominator indicated power in ISFC formula is more than the brake power in kilowatts in the BSFC formula. Therefore, ISFC shall be lesser than BSFC. Now we can define mechanical efficiency again here as ISFC by BSFC. Now the mechanical efficiency has got totally the different formats: BP by IEP, brake thermal efficiency divided by indicated thermal efficiency, and ISFC divided by BSFC, and it can have another format, that is BMEP by IMEP, that is where BMEP is equal to brake mean effective pressure, and IMEP is indicated mean effective pressure. When we are calculating, here important note is, when brake power is calculated based on given BMEP value, we have to consider N or N by 2 distinguishing based on 2-stroke or based on 2-stroke or 4-stroke cycle engines, and also take into account number of cylinders, that is brake power has got another formula. Brake power in kilowatts is equal to PM brake, that is brake mean effective pressure, into LA into N by 2 or N based on 2-stroke or 4-stroke engines into K. This is the formula for 4S engine, 4-stroke cycle engine. Again, this is equal to PM brake into LA into N by 2 by 60 into K for 2S engine. Here N is RPM, K is number of cylinders, and LA is V-stroke or stroke volume. PM is in brake mean effective pressure in kilopascals. Stroke volume should be in meter cube. Then the resultant answer will be obtained in kilowatts. Now let us solve a problem given in GATE 1997 regarding IC engines. Conventional problem. The power output of an IC engine is measured by a rope brake dynamometer. The diameter of the brake pulley is 700 mm and the rope diameter is 25 mm. The load on the right side of the rope is 50 kg mass, and the spring balance reads 50 newtons. The engine running at 900 revolutions per minute consumes the fuel of calorific value 44,000 kilojoule per kg at a rate of 4 kg per hour. Assume G is equal to 9.81 meters per second square. Then calculate A brake specific fuel consumption, B brake thermal efficiency. Now the given problem can be solved in this fashion. Let us pictorially represent the data given. This is the brake drum, rope wound around the brake drum. This is the spring load. This is a dead weight. Dead weight is given as 50 kg mass, implies weight is 50 into 9.81 newtons. The spring load S is given as just 50 newtons. This is a crankshaft. Key to the drum. The diameter of the drum is given as 700 mm. Therefore, radius is 350 mm. The rotational speed of the engine is given as 900 rpm, revolutions per minute. Now, first of all, let us calculate brake power in kilowatts by using the formula. Brake torque into angular velocity. Brake torque is W minus S net brake load into brake mean radius, that is a brake torque, into angular velocity is 2 pi n by 60, that is 50 into 9.81, that is the W, minus 50 into mean radius is 350 mm. Let us convert that into the meters, divided by 1000 into 2 pi into 900 rpm, that is by 60. Whole should be divided. The load also I will divide with 1000, so that because the loads were given in newtons, I want to convert it to the kilonewtons. The resultant answer is brake power will be obtained directly in kilowatts. Then brake specific fuel consumption. BSFC is equal to fuel consumed in kg per hour divided by brake power in kilowatts. Fuel consumed in kg per hour is given by 4, divided by BP is just obtained above. We get the answer in kg per kilowatt hour. Now let's calculate brake thermal efficiency as brake power in kilowatts divided by mass consumption rate of the fuel into LCV. This where m dot f should be in kg per second and LCV should be in kilojoule per kg. Mass consumption rate of the fuel is given as 4 kg per hour. Divide with that 600, it becomes kg per second. LCV is given as 44,000 kilojoule per kg. Brake power is already obtained above, so we can obtain the brake thermal efficiency. It will be around in the range of 25 to 30% answer. Usually that is a brake thermal efficiency range for an internal combustion engine. Now I shall solve a problem on IC engine given in GATE 2000. This is the problem on IC engines given as a diesel engine develops a brake power of 4.5 kilowatts. Its indicated thermal efficiency is 30% and the mechanical efficiency is 85%. Take the calorific value of the fuel as 40,000 kilojoule per kg and calculate A, the fuel consumption in kg per hour, and B, the indicated specific fuel consumption. Now I shall give the solution like this. The data is given as brake power is given as 4.5 kilowatts. Because the mechanical efficiency is defined as brake power divided by indicated power, implies indicated power is BP by mechanical efficiency, which is given as 85%. That is 4.5 divided by 0.85, that gives the indicated power in kilowatts. Now the indicated thermal efficiency is given as 30%, which is equal to 0.3. This is equal to indicated power in kilowatts divided by m dot f into LCV, where m dot f is mass consumption rate of fuel in kg per second. Therefore m dot f is equal to IP in kilowatts divided by indicated thermal efficiency into lower calorific value of the fuel. Indicated power is already obtained above. Indicated thermal efficiency is given as 0.3, and the calorific value of the fuel, lower calorific value, is given as 40,000. We can obtain m dot f in kg per second. But since the data asked is regarding kg per hour, multiply this with 3600, we'll get the mass consumption rate of the fuel in kg per hour. The indicated specific fuel consumption is equal to ISFC is equal to fuel consumption in kg per hour divided by indicated power in kilowatts. Because indicated power is already calculated, fuel consumption kg per hour also we calculated. We can easily calculate ISFC in kg per kilowatt hour. This is hence the problem. Now let us solve another objective question regarding the Otto cycle. Consider the following statements regarding Otto cycle. Number 1. It is not a reversible cycle. Number 2. Its efficiency can be improved by using a working fluid of higher value of ratio of specific heats. Number 3. The practical way of increasing its efficiency is to increase the compression ratio. Number 4. Carbureted gasoline engines working on Otto cycle can work with the compression ratios more than 12. Of these statements, A. 1, 3 and 4 are correct. B. 1, 2 and 3 are correct. C. 1, 2 and 4 are correct. D. 2, 3 and 4 are correct. The Otto cycle is a reversible cycle, because in the ideal Otto cycle we do not assume any frictional losses. Now coming to the next step, first is correct. Number 1 is correct. Coming to the second statement, its efficiency can be improved by using a working fluid of higher value of ratio of specific heats. Thermal efficiency of Otto cycle is 1 minus 1 by R to the power of gamma minus 1. As gamma increases, thermal efficiency of Otto cycle also increases. That is, second statement is also correct. The practical way of increasing its efficiency is to increase the compression ratio. As R increases, that is the compression ratio increases, thermal efficiency of Otto cycle increases. That is also correct. 1, 2, 3, all the 3 are correct. But as coming to the fourth statement, carbureted gasoline engines working on Otto cycle, they would never work with a compression ratio more than 12. So fourth is wrong. So answer is 1, 2, 3 are correct.